Thank you. So yeah, I've been a CITA fellow since, I guess, the fall of 2017, but this is my first visit here, and it's very nice to be here. It's very nice meeting all of you. It's been very hospitable. And I, of course, won't be a CITA fellow past August of this year, and that is because just today I've accepted a tenure-track faculty position at Illinois State University, and I'm very proud to announce that to the world for the first time. And I owe a debt of gratitude to CITA for having me as a national fellow. That really allowed me the freedom to explore my research interests and develop my research program that allowed me to secure this position. So I owe a debt of gratitude to CITA. With that said, let's dive into the research that I've been doing as a fellow. I study astromaterials, and that's kind of a made-up word. So maybe before defining astromaterials, we should just define materials. So when I say a material, what's the first thing that comes to mind?
Piece of iron.
A piece of iron, okay, so like a crystal, a metal and crystal. This is sort of fibers that are woven together in some way. What are other materials that come to mind when I say materials? Anybody, shout something out.
Fabric.
Fabric, great, okay. Am I a material? I'm certainly not a puddle on the floor, right? Like I have some sort of squishy material and there's bone in me. So materials take a lot of different forms. And if you go on the Wikipedia page, or at least when I first did this bit, if you read the Wikipedia article for material science is the science that is concerned with materials. And then when you go to the materials page, it says materials are the things that are the subject of material science. It's completely circular and it's completely unhelpful. And so I have this definition that I like, which I propose, and you don't have to take it if you work on materials and you prefer a different definition, that's fine. I like to call a thing that's a material is a thing that's not fluid. Okay, so that's what I mean by puddling on the floor. Something about materials, they have very slow diffusion and they just tend to stay put. Whether it's Jell-O or me or a table or iron, that's what I think of as a material, not water. Say again?
Shear stress, that's the only...
Exactly, something that can resist shear stress in a way. And so when I prepend it, I give it this astro prefix, what I mean to tell you is that stars freeze. And even for astrophysicists and people that work in the field and have been doing this their whole lives, that can sound kind of weird. So I'm an astromaterial scientist, which means I study how stars freeze and I study the material properties of things in stars. So maybe I should tell you how to get to the point where a star freezes. Everybody kind of knows this in this room, right? A star burns hydrogen to helium and kind of works its way up the periodic table until the most massive stars make these cores of iron. And iron is nuclear ash. You can't squeeze any more juice out of iron. So it just kind of builds up in the cores of these massive stars until eventually it's going to implode in a supernova. So when that happens, the pressure support from the core kind of gives out. And you take all these iron nuclei and they're surrounded with electrons. And the electrons kind of get squeezed into the protons. And what this does is it makes a rush of neutrinos and then basically makes a very large number of neutrons with some mix of protons thrown in. And then without that pressure support, they collapse into this blob of kind of a nuclear matter, mostly neutrons, a few percent protons, with some electrons sprinkled in. That was 5 nuclei. This is happening to 10 to the 55 nuclei all at once. And so all of those neutrinos come streaming out, and you sort of blow the outer layers off of the star, and kablowie, that's a supernova, right? Here's the crab 1,000 years after it went off. And this little guy right here, that's a supernova. They can outshine their host galaxies for about a week. Can't have a talk about supernova and neutron stars without these figures. Okay, so at that point, the star's dead, right? You've made a neutron star at that point, and it's just going to cool off. There's really nothing left for it to do except cool. So I just want to talk for a second about the scale of one of these objects in the event that you are not neutron star astrophysicist yourself. Consider the difference in length scale between an angstrom, about an atom size, to a nuclear length scale, femtometers. That's 5 orders of magnitude in length. So that's going to be 15 orders of magnitude approximately in volume and density. So that's really incredible because it means that they're so dense that Mount Everest would fit in a cup of coffee. Every living human could be squeezed into the size of a sugar cube if you dropped them onto a neutron star. And of course, as always, you have to drop the solar mass neutron star on your current location. If you dropped a solar mass neutron star on us right now, it wouldn't even reach Markham. They are incredibly compact objects, and they're these incredibly rich laboratories for nuclear physics. OK, so when we do outreach, what's a nucleus, or what's a neutron star? A neutron star is like a giant nucleus in space. And that's exactly what I just showed you like 5 slides ago. And now I want to take that one step further. So if you remember one thing from my talk, let it be this. Neutron stars have substructure. They have a crust. They have a magnetic field. They have all of these components that are in many ways similar to the Earth. So imagine you go up. So let's consider the Earth for a minute. Go up and start at the top of the atmosphere. It's basically the vacuum of space. There's nothing around. And then start to descend, start to drop. And what you're going to experience is an increase in pressure. It's an increase in density. It's an increase in temperature as you descend through the atmosphere of the Earth. And you go down and you go down and you go down, and the pressure and density keep rising until you hit this thing that we call the ground. There's this first order phase transition, and you hit kind of rock in the case of the Earth. And then if you keep going down, eventually it starts to get very tacky. There's this kind of gooey layer, which eventually gives way to a fully liquid core. And neutron stars, rather surprisingly, have a similar structure, rescaled a bit, but quite similar. So if you were to fall onto a neutron star, you would experience something very similar. There's an atmosphere, a thin envelope, which is effectively gaseous, where the temperature the density and pressure are rising as you descend through them. You hit a solid crust, and then in that crust, the pressure is so high that despite being 500,000 Kelvin surface temperature, the pressure is great enough to force nuclei into a lattice. There's no electron bonds or anything. It's all fully ionized. But there's a solid lattice, which then gets squeezed together as that density goes up to 10 to the 14 grams per cubic centimeters until eventually it all mushes together in the core. And so that's the anatomy of the outer kilometer or so of a neutron star. Why should you care? That is a great question, complete straw man of an audience member that I will now address and knock down. Why should you care? The crust has material properties. It has a thermal conductivity. It has an electrical conductivity. It has elastic properties. And all of these material properties should affect observables of the neutron star. And so that's basically my shtick. I'm a theorist who studies the crust, who applies material science techniques to the crust to try and get at some of these material properties so that we can interpret observations. If you don't understand the crust, how can you interpret observations that might tell you what's in the core, which could tell you fundamental things about the nature of nuclear physics and matter in the universe? That's my shtick. That's why I do what I do. OK, I'm going to talk about 2 or 3, time permitting, things that I work on. And the first is a relatively new problem that I've started to work on, which is crust replacement. So there are these systems called Xray binaries. This is not drawn to scale, but the idea is that there is a neutron star in a binary with some other object. And that big, hot, either main sequence or giant companion star overfills its Roche lobe, and then an accretion disk forms, which funnels matter onto the surface of the neutron star, and the neutron star accretes. So accreted matter arrives on the neutron star, it burns, it produces some heavy mixture, and then it's buried by later arriving material. So you could imagine if there was constantly dust and asteroids falling from space that completely buried the surface of the Earth, eventually you would have a kind of new crust that would come from this material that's fallen from space. So the same thing can happen on a neutron star, and actually does in these systems, which is that if you accrete at 10 to the -8 solar masses a year for 1 million years, you can accrete a crust mass, and you can completely replace the crust with this new material. OK, so as the accreted matter is buried, it's going to descend. And as material descends through the crust and is driven to high pressure and density, it'll undergo nuclear reactions which release heat. So for those of you who happen to be neutron star theorists, you're probably familiar with this. Electron captures will process a nucleus to be more neutron rich. Once you've hit the neutron drip line, you will actually emit neutrons and you will shed them into a gas. So you will have a gas of neutrons around your nuclei. And then there are these things called pycnonuclear fusion, which happen at really high densities. At this point, the nuclear wave functions overlap sufficiently that there's a non-trivial probability of just spontaneous tunneling that they'll fuse. So this is cold fusion by any other name, just spontaneous fusion at densities of like 10 to the 12, 10 to the 13 grams per cubic centimeter. And again, to emphasize, all of these reactions release heat. They release heat of different amounts, and they release heat at different depths in the crust. And so all of that needs to be known in order to interpret observations of neutron stars in accreting binaries.
Here you assume that the hydrogen and the helium have already fused higher up.
Oh yes, so this is the ocean. So the burning is going to happen in the ocean and produce.
Carbon is 10 to the 9, so you're thinking much heavier.
Yeah, so I'm going to run through a toy problem in a second, but there's all of the X-ray burst phenomenology and all the RP process burning that happens here in the ocean, which is then buried by more hydrogen, and those heavy things then settle into the crust. Yeah. Okay, so let's walk through the crust. This is an iron nucleus. This is some product of burning, which is now going to be deposited at that interface of the ocean and the crust, and it's going to get sent down as more material piles up on top of it. So you are here. You're sort of at the top of the crust. Here's my crust, and then down here's the core. There's an electron gas, a relativistic degenerate electron gas around, and as you go up in density and pressure, your electron Fermi energy is rising, and that's going to drive electron capture. So the electrons will capture on the protons and make your nucleus increasingly neutron rich. This is going to happen again and again as you descend until your nucleus is so neutron rich that you have pushed all the way out to the drip line on the table of nuclides, and any further electron captures immediately result in neutron emissions. So then you have a neutron gas that sort of surrounds or is a sort of a bath surrounding these nuclei. And you can continue going to higher pressure, and the same processes will continue until those spontaneous fusions can occur. Two nuclei will spontaneously fuse, and what happens is that very quickly that second nucleus is then processed mostly into neutrons and are shed into the gas as well. And so this continues. This can happen a few more times. Multiple pycnonuclear fusions is pretty normal until you're at such high densities, you're basically at core density, and then the nuclear separations are comparable to the nuclear radii, and everything kind of gets very fuzzy, and nuclear physics gets kind of hard. And this is sort of the very base of the crust before they all get smushed together into one blob, which is the core. Okay, so everything.
You draw just neutrons, but roughly 8 of them would be protons also. So will this change the picture?
It depends on exactly which nucleus is present. The proton fraction is about maybe 10%, depending on the exact equation of state or nuclear model you use.
I guess your point is that above, at lower densities, all the protons are still in nuclei.
Right.
They're not free yet. It's just the neutrons that become free. Right?
Yes, the protons will remain bound. The protons won't form a gas in the same way.
And they're even higher.
Yeah. Okay, so this is a problem that I've started working on in kind of the past month or two. So I don't have much in the way of big, shiny, new revolutionary results to present. But I will show you what I've been working on, which is to calculate these mass chains for a given input nucleus. So what I just showed you with the cartoons was an example of an iron 56 nucleus being driven to depth. So to read this in with that picture in mind that I just showed you, start with an iron 56 nucleus. Here's the mass, here's the charge, and send it this way, going from low density to high density. And what you'll see is that there are these little stair steps which correspond to those electron captures. Your nucleus is becoming more neutron rich until eventually this stair step pattern where you capture 2 electrons and you also emit 2 neutrons. So this is the start of that neutron emission. And that continues, and the nucleus shrinks and continues to get smaller. And then the Coulomb barrier kind of disappears, and they can fuse. And so these jumps correspond to those spontaneous pycnonuclear fusions, which happen. And eventually, it all gets sort of mushed together and drives up as you push it into the core. And here's the exact same thing for a different nucleus. This is magnesium-24 being driven to depth. You see 1 electron capture here, and then the pycnonuclear fusion starts at a much higher density because of the lower charge to begin with. And something to notice here is that I've included these stem plots. Q, that thing that I'm reporting there, is the heat produced by each of these nuclear reactions. So what I'm doing is I'm producing a map of where heat is deposited as a function of depth and density in the crust due to the accreted material. So this is exactly what an observer might want to put into their model of an accreting binary in order to interpret the thermal evolution of that system.
So there's no real loss associated with the neutronization? Because I guess you're emitting a neutrino, so there's energy being lost from the system, or is it?
Yes, so that's a really good question. For a long time, mostly what I'm doing here is I'm duplicating known results. Right, so to answer your question about neutrinos, for a long time people assumed that most of the energy was lost to neutrinos, especially in these electron captures. That has since been revised in the past few years because we now think it's more likely that you're electron capturing to an excited state and then decaying, and that will result in, I guess, less energy to the neutrino. So we think the bulk of the energy from these electron captures does go into the crust now. And then the second point is that neutron emissions and the pycnonuclear fusions, most of that energy goes into kinetic energy of the daughters of the neutrons and so forth. So these really big stems, which are associated with those pycnonuclear fusions, we have confidence that that's real in a way. That's a really sharp question, thank you.
Small fraction of the energy that you get just from depositing something on the surface, just from accreting this atom onto the surface of the neutron star. So how would you observe such a small energy deposition?
So as it's done in models, they observe these systems and they are sensitive. I'm just saying they as observers who I talk to. They are sensitive to fluctuations of plus minus 1 MeV in deep crustal heating in order to actually fit the light curves. So all I'll just say is
wait for the accretion to stop, and then see how these systems in quiescence.
And you also wait from the being quiescence, and you can see it then.
It's not that they're accreting. It's not that they've done accretion or they've done away for a while. The accretion is.
Yes and no. Both the quiescent sources are good to interpret this, but also to interpret them when they are in outburst, when X-ray bursts are happening, you do need to know where order MeV heat sources are showing up in your problem.
So when you introduced this, you said crust replacement.
Yes.
This sounds like individual events within a medium called the crust is not changing.
Yes. So what I've you're exactly one slide ahead of me, thank you. So what I've described here is single profiles of crusts that are being composed of one composition coming in. So you can imagine if iron 56 has been coming in for 1 million years, the crust will look like this, and this is a steady state for the accreting system. Okay, so now suppose that the accretion rate changed in such a way that the burning is now producing a different product in the ocean. All of this will cease to be true as some new crust comes through and replaces it. So that's exactly my next slide, which is that the crust can be replaced over the lifetime of the binary. So what's a good way to think of this? Imagine you have completely finished stripping the hydrogen envelope of your companion, and now you begin to accrete something that's more helium-rich. And when you do that, your burning in the ocean is obviously going to change. So you'll have some new mass chain and new crust profile that's going to be built on top of the old crust. So there's an interface corresponding to some astrophysical event, which then moves down through the crust as the crust is replaced. And so this is what I mean by crust replacement, is this is something we might hope to observe is a source whose deep heating can't be understood presently, but might be better understood by having a masked, invisible previous crust that is being replaced. So I will give you a short movie to show you what might happen as to the crust composition as this interface moves down. So let me see if I can give you this little animation. So this is, again, the magnesium-24 mass chain that you just saw. And what you're seeing is a krypton-86 crust replacing it. So I'm going to show that one more time. So sort of watch as the new crust comes through and then sweeps away the old crust as the old crust is then mushed into the core. And so that is more or less what would happen in an event of crust replacement. And the thing to keep in mind is that this heat is changing. As this interface moves through, capture layers or neutron emission layers are going to shut off, and new nuclear reactions are going to turn on as the new material reaches that depth. So watch as these stem plots, these large capture layers are going to turn off as that interface sweeps through, and new reactions turn on in their place. Did I push the button right? This layer shuts off, and new heat sources turn on. So what this can result in is large fluctuations in the heating over the timescale of crust replacement. So this plot is basically showing you from starting with entirely the original crust and completely replacing the crust as that interface moves down. How does the heat fluctuate in the crust? And sure enough, you do see these order MeV variations that can occur, especially during the early time of the crust replacement, which should be observable. Order MeV fluctuations in crustal heating sources should absolutely be observable. And so this is something that is still very much so a work in progress, and I don't have much more to show than this. But observers have been talking to me about this, and we're very excited to sort of write this up and start putting it into fits.
You get the same effect if you have, I mean, you're starting with krypton 86, but at a density of 10 to the 7, 10 to the 8 coming down, which isn't realistic, right? I mean,
I don't understand the question. Why not? Or
well, how do you get tons of krypton 86 at a density of 10 to the 7?
So 10 to the 7 is sort of a low density for me. No electron captures will kind of happen before that. Yeah. So you still just have whatever is made in the nuclear burning at those densities. So I don't really need to see anything above here because there's no heating up this high.
The process could really produce tons of.
It can produce very different things, and it's strongly dependent on the accretion rate and the hydrogen to helium ratio of the incoming mixture. So you really can, if you start to accrete faster or slower, that'll produce very different mixtures from the RP process, even up to tin or antimony, but sometimes as light as magnesium.
So that composition is actually quite uncertain.
Yes, and that's
for any given source, you will not know the past accretion history.
Exactly. And this is something that observers struggle with, is they have of order MeV inexplicable heat sources that they need to understand in the deep crust. And it could be possible that crust replacement is some way to explain this with completely conventional ideas without resorting to new physics to get new heat sources.
So what's the typical diffusion time for an atom to get from the crust to the core?
That's going to depend on your accretion rate. So the faster you're accreting, the faster you can replace the crust.
Just a single one, just a single atom. What would be the diffusion time?
So it's not necessarily diffusion time. It is going to be. It's sort of like putting a block on a conveyor belt, and then the conveyor belt carries it to the core because there's more of it.
The order of magnitude sense of what the diffusion time is.
Yeah.
Sure. So if it is 10 to the minus 8 solar, that's Eddington, I think, is 10 to the minus 8 solar.
That's the true diffusion time. That's what you're comparing against. So how smoothed out is this?
Oh, the diffusion time is practically none. I mean, yeah, the density and pressure gets so high so quickly once it freezes that the diffusion might as well drop to 0 effectively. It's
basically a lattice, right? So I think that's sense.
I'm actually working on a paper on diffusion in these systems right now, funny enough. But yeah, it goes to 0 very quickly once it freezes. It's just the pressure gets so high that they're not going to move. So let's see. Yeah, so that's just kind of the same idea again, but I'll just sort of to sum that up. It's an unstudied feature in X-ray binaries, and it may have immediate implications for interpreting observations. So this is what some of the observers I've worked with on this have called low-hanging fruit. And so I'm really looking forward to kind of working on this more in the next year. Obviously, there's plenty of opportunities to work on better mass models and studying mixtures, especially instead of just this single nucleus approximation that I've been using. And of course, comparing to observations.
But it cannot not move, right? Because it radiates. If it radiates, then you have to move from one quantum state to another.
Sure.
So something has to move. There has to be motion. So the diffusion time cannot be infinite in this case.
You're asking for a particle diffusion time or a photon diffusion time?
No, just a
particle.
Heat transfers by relativistic.
No, I'm talking about if you put just a particle there.
But if it's just lattice, why would it move?
So this is a very, very good question, and I do encourage you to talk to me more about this later because I actually am working on the diffusion coefficients of nuclei right now. So this is a very good question. I do want to talk more about this. So I'll just mention I do other work on these problems too, in case some of you happen to work on similar things and would like to talk about them. I do molecular dynamics. These are direct simulations of these mixtures that come from burning. So this is a view of one of these lattices. The different colors, if you can see them, are to show different species, different nuclei in the mixture. And of course, I also study the chemical separation. So this awful looking triangle is a phase diagram to study how alloys form at the base of the ocean and how it separates. So I also do a lot of other things, material science on the crust as well. So molecular dynamics, phase diagrams, if any of that interests you, talk to me about it. I'm here all week. OK, I will move on now to my second main topic of research, which is nuclear pasta. So I mentioned that there's this base layer where the nuclear separation becomes comparable to the nuclear radius. And at those depths, nuclei start to touch and they'll rearrange. So at the top in the crust, you have nuclei that are distinct spheres that are sort of isolated drops of nuclear matter. And then the core is this bulk nuclear matter. So there has to be some kind of nuclear phase transition where nuclei start to touch. And that's what we call the pasta. So if you take spheres and you sort of smush them together, you make these cylinders, spaghetti. And if you take these sort of spaghetti strands and you sort of smush them together, you make these plates, these parallel plates of nuclear matter, lasagna. And you can eventually smush them together and you get this kind of bulk matter with tunnels and bubbles in it. And this is all happening right at the base of the crust. So this is kind of the densest material in the universe. It's 10 to the 13 and some change grams per cubic centimeter. OK, so how can you understand what's happening there a little bit more intuitively? There were these two theory papers from the early 1980s which just sort of took or considered the Coulomb repulsion between protons, sort of the Coulomb energy of different shapes, the volume energy of nuclear matter, and then the surface energy. And so there's this proton-proton attraction which repels and pushes outward. And then there's a nuclear attraction between all of the nucleons which smushes you together. And at high densities, you can lower that Coulomb energy a little bit at a tax of surface energy by taking on these non-spherical shapes. So we've taken to calling these kind of gnocchi, spaghetti, these planes or lasagna. I like to call the cylindrical tunnels anti-spaghetti, and this is anti-gnocchi in my nomenclature. But it's all just about minimizing the energy of the nucleons. So I'll explain this more in a moment, but these are those figures from 1980 that were sketched out. These are some of my simulations that I did in my PhD. This is remarkable agreement between theory and more theory. So again, to help you get oriented just a little more, I want to show you an animation of this. So what I'm going to do is I'm going to show you a block of, this is basically pure nuclear matter. This is kind of core density stuff right here. And what you're going to watch is this simulation volume is going to expand. And I'm going to decompress it. And the density is going to go down. And we're going to sweep through the phases of pasta matter that would happen at the base of the crust. So imagine you're starting at the core. And then you're going to go up to the crust. This is also coincidentally what it might look like when matter is ejected from these depths in a neutron star merger. So very early, you see these bubbles open up. They form a nice lattice in the material, those Antinokey. They fuse to form tunnels, that anti-spaghetti stuff I mentioned. And eventually, all of the walls break down between those tunnels, and you just get these plates, these kind of lasagna plates. This is all at finite temperature, so that's why you're seeing these fluctuations. So these are all sort of sheets of nuclear matter. I'm sorry if anybody missed lunch. This must be awful. Eventually, those plates fission. It's a first-order phase transition, and you get the spaghetti. They, again, are thermally fluctuating. There's this nice hexagonal packing. They make a nice lattice as well, if you look on that face. And then right around now, they're going to start to fission, and you're going to just be left with these distinct little droplets, these gnocchi, or essentially just nuclei, which also themselves form a lattice. You could see sort of the Bragg plane right there. And now we're kind of back to the inner crust. We're sort of to the top of the pasta layer now. And again, this was sort of a length scale here. All of those pasta structures were happening on nuclear length scales.
So when you increased the volume, did you keep the entropy the same, or along what thermodynamic trajectory do you?
It's isothermal.
So why, when you inject it, would you get the same? Would they follow the same trajectory?
It would be modified a bit. It wouldn't necessarily follow that exact path, but
it would be an adiabatic
It would be adiabatic in that case, yeah. So how do I do these simulations? I do molecular dynamics again. So this is to give you a bit more detail about some of my MD simulations. This is far easier than calculating wave functions and doing big simulations of quantum mechanically. So these are a bit like Leonard-Jones interactions. I have potentials for the neutron-proton interaction, neutron-neutron interaction, and proton-proton interaction. So there's a very strong nuclear attraction between protons and neutrons. This is much weaker. Protons have this added Coulomb repulsion term. All of these parameters are just chosen to reproduce binding energies of nuclei, the energy of symmetric nuclear matter and pure neutron matter. So it's a pretty well-fit model, I think, theoretically. And all it boils down to is calculating the energies of interactions for short-range nuclear interactions and then including these long-range Coulomb repulsions between protons.
It's like a hydro calculation, or is this?
It's MD. They're particles. Yeah, it's so a bit like a hydro calculation. Yeah. So yeah, everything that you just saw, all those nice yellow surfaces, those are sort of surfaces of isodensity, sort of drawn around the blobs. So that's how I made those simulations you saw before. But inside them, it's actually just these little balls bouncing around. And that's all formalism. You can kind of just forget that because it's not going to matter in a moment. Really think about the thermodynamics again. There's really three knobs on the model. There's the density, there's the temperature, and then there's the ratio of protons to neutrons. If you uniquely specify those three thermodynamic quantities in some model, then you should be uniquely specifying the phase. And so for me, that phase is something geometric. OK, again, Mr. Strawman audience member, why should I care? Well, the material properties of pasta should affect a very large number of astrophysical observables. And I think that basically every single one of these topics that I list here, there is something in the literature where people discuss the role of nuclear geometries on this astrophysical transient. So for example, the thermal properties, how thermally conductive and the heat capacity determines how the crust cools in Xray binaries as a cooling wave passes through the pasta towards the core. There's papers that suggest that the pasta is electrically resistive, at least relative to some of the surrounding layers, and that could result in electric currents dissipating by ohmic scattering, and that can cause magnetic fields to decay in magnetars. So it's been proposed that pasta being electrically resistive is one explanation for the absence of slowly spinning magnetars. It's why their field decays away quickly. Gravitational wave amplitude, that's actually one that I've worked on most recently. If pasta has sort of some rigidity to it, if it has some structure and it can support itself, you can make a mountain. Admittedly, a buried mountain, it would be a lump very deep in the neutron star. But that's a lot of mass, right? I mean, this is something, the mass of the Himalayas and a cup of coffee again. So if you spin that neutron star 100 times a second and you have that big of a lump, that's a continuous gravitational wave source. So LIGO is actively looking for continuous gravitational waves from lumps on neutron stars. In breaking, if pasta can shatter for some reason, we have all considered star quakes and other breaking mechanisms in neutron stars before.
If you expect one lump, then you should expect also, like, but you're saying that this would give you a large signal if you have just one, but if you have multiple of these, then you would have multiple.
Yes. So if you do have just sort of noise in the surface mountains, they shouldn't add coherently. So what you do want is you want some mechanism to give you a large asymmetry in one hemisphere, perhaps due to the dipole moment of the magnetic field. You would want one sort of hemisphere-sized lump to be locked in.
The magnetic field that would break.
Yes, that's a very good point.
The symmetry.
Right. You would want just one really big mountain, not lots of little ones all over. The pasta spacing, so this length scale of a few, maybe 10 femtometers, that can be comparable to neutrino wavelengths during supernova, a few seconds post-bounce. And that can result in neutrino trapping. And this could have a significant effect on neutrino transport and heating in supernova. This is something I am really interested in looking at. And I've got a few colleagues. We want to put pasta neutrino opacities into supernova models and see how that affects them. And then lastly, like I said, pasta could decompress and form R process seeds and affect the neutrino transport in the R process as well.
Which one of these comes? If you take a cross-section of 10 to the minus 40 centimeters squared, so what would be the optical depth of each one of these?
I don't know that number off the top of my head.
The
Yeah.
neutrino's small.
Yeah, so I'm wondering why would it matter so much, right? There's a bunch of
Oh, but
This-
it's coherent back to
It'd be coherent scattering, yeah. Okay, so I said that this was the one I've worked on most recently, so this is the one I'm going to talk to you about. So what are the elastic properties of nuclear pasta, and why should they matter? So the strength of astromaterials should affect a number of both gravitational wave and electromagnetic signals. So for a long time, people have just taken that the effective shear modulus of the neutron star crust, you can just kind of extrapolate what's known for ions in a lattice to these high densities. But really, nobody knew when they were plotting this curve that it should be strong or if it should drop off for some reason. This is just extrapolating what they liked. So I sort of set out to kind of put a data point here so that we could either change these curves or trust them a bit better. So why should this matter? Well, like I said, lumps, if you can put a lump, this is really exaggerated on a neutron star, and then spin it 100 times a second, that's continuous gravitational waves. And then another one, which I really, really like, this comes from David Tsang, who was a postdoc at McGill, actually long before I was there. But he proposed that during a neutron star merger, the tidal forces could shatter the neutron star crust just prior to the merger itself. So there could be GRB pre-flares associated with crust shattering in the seconds before a neutron star merger. And so there's some archival data that there are SGRBs with precursors. 170817 wasn't one of them, unfortunately. But it's just something that the elastic properties of pasta and the crust itself could affect this specific electromagnetic transient, which is predicted. So there's a lot of really rich astrophysics to be had in the elastic properties of the crust. So I've shown you a lot of pictures of perfect pasta, these kind of nice stacked up things of lasagna. And I haven't shown you some of these slightly less nice looking pieces of pasta, which are these things that have these defects woven through them. So these are sort of filaments that connect these different plates. But I want you to imagine a shear force applied to each of these systems. If I had a deck of cards in my hands, if I had a deck of cards and I flicked it, they're going to go everywhere. And I'm going to be playing 52 card pickup because they don't really resist a shear force. But if I have something that connects them, if I sort of run a glue stick along the edge of that deck of cards and then I wrap it in a sheet of paper and I've made like a little book out of it, I bind it like a book. If I flick a book, it sort of goes and it doesn't spill everywhere because it can resist that shear force. So these defects can actually produce an effective shear modulus in pasta. So I did some simulations kind of last year to tease out what the different elastic properties of some of these phases and structures might be. And so it's very similar to that simulation I showed you before. This is kind of an old slide. I'm not going to really show you exactly this. But it's 3 steps. I deform the simulation volume, just like in that one video I showed you. I calculate the stress. It's just a virial expansion. It's a standard technique in molecular dynamics. And then that lets me have some kind of pressure curves, the pressure tensor, which I can then extract elastic moduli from. So I'm just going to show you one of these videos. This is a block of nuclear pasta. And these things in the foreground, that's not actually the plate. Those are actually those filament defects. The plates are actually these things oriented this way. If you sort of see them, the plates are behind here oriented like this, and these are defects. So I'm going to extend this simulation, and that's going to induce a shear stress between the plates as they try to adjust their inclination in the simulation volume. So what you're watching is those filaments breaking away as the filaments or as the plates sort of shift. I'll show it one more time. And snap. So that's actually enough for me to extract a shear modulus for those plates with those little filaments in them. These are the stresses. These are principal stresses sort of along X, Y, and Z. These are tensile stresses. These are shear stresses. So the shear stress that you're seeing in the XZ plane, this dip right here is the shear stress due to those filaments kind of pulling back on the plates. And so it's of order 10 to the minus 4 MeV per cubic femtometers is kind of the number that I get for that. That's not a very helpful number. So in ergs per cubic centimeter. That's like 10 to the 31. And that is the largest shear modulus reported in the literature for any material. So I actually, in the abstract of the paper, said that, and I pointed out that this amusing coincidence that it's the largest reported shear modulus. That just comes from the equation of state, but it's going to be comparable, but it's going to be a bit higher. It's going to be way higher, yeah. Yeah, and I reported that in the abstract, and the pop media loved it. They're like, the strongest material in the universe is pasta. And there was a really enormous amount of pop sci press that came out of it, but many of them were very good journalists who wrote good stories.
The sigma XC curve is continuing to increase.
Yes. So that's due to this is mechanical engineering speak. It's the principal stresses have actually been transformed into a shear stress here because the plates are misaligned with the box. So I have another simulation which I use to subtract out this growth and just extract this. So it's this little bump, but yeah, what you're seeing here is a tensile stress transformed into a shear stress due to the orientation of the material in the box.
But you're stretching the box. That's the
right.
Your computational input, and you're measuring the stress as a function of.
As a function of the linear strain, of the tensile strain, yeah. It's not perfect. I will just freely admit up front, this is like a very hackish way to do this.
The remainder of this curve is important, isn't it, or is it not?
No, what you're seeing here is the tensile strength of the material.
Okay.
Yeah.
Got it.
Okay, so what I just showed you was sort of a unit cell of kind of perfect material. And you can think of that as like a grain of a monocrystal. But maybe pasta isn't perfect all the way through the star. Maybe if you look at large enough length scales, like in a lot of terrestrial materials, there's defects. And so locally, maybe it looks like this. Maybe it's perfect locally, and there's nice, smooth material. But if you look on a large enough length scale, if you zoom out and if you do a big enough simulation, maybe you'll see domains and sort of long scale fluctuations. So maybe pasta bending and defects could affect the elastic properties. So I wanted to look at an angle average system with many domains. So I'm going to show you what I describe as a polycrystalline sample of nuclear pasta. OK, this is a simulation with 3.2 million nucleons, protons and neutrons in there. For scale, this is the simulation I showed you a second ago. This is 100,000 nucleons. So this is going up almost 2 orders of magnitude in size. So all of these different colors are being used to identify regions where the pasta plates have a different orientation. So you can think of them as like domains, and then the edges between them are a bit like domain boundaries in a conventional material. So I should take a moment and emphasize that my co-author, Andre Schneider, currently a postdoc in Stockholm, is the one who is responsible for making these very beautiful plots and working out the algorithm to do the domain recognition. He's a very talented computational physicist, and he deserves an enormous share of the credit for these figures. So what I'm going to do is I'm going to take this box with a bunch of these kind of different domains, and I'm going to squeeze it. No, this was actually, that's a great question. We started from random, and we just let it equilibrate for millions and millions of time steps. And this is kind of where it got stuck. It didn't really keep equilibrating or relaxing. Yeah, the characteristic size scale is about 10 times the pasta spacing. And it turns out that there's this, it's named after Landau and someone else, for the smectic A liquid crystal, which technically this is. It's a liquid crystal, guys, I admit it. That the characteristic fluctuation scale given our model is going to be about 10. So we actually match this liquid crystal prediction if you just pull out Landau's text.
So it's a function of the temperature.
And it's going to be a function of the temperature too. So I'm going to pull on this box. And I encourage you to just pick a domain and focus on it and watch what happens right around now. You're going to notice that the domains are now going to start shrinking or growing as material is exchanged across the boundary. So right around strains of about 15%, they start to deform plastically as material flows from one domain to the next. And this could also be, I'd really love to do more simulations like this to kind of anneal and see how it evolves through multiple cycles of this. Unfortunately, this was something like 30 million GPU hours to evolve, and it's really not going to get any cheaper. So this is kind of a one-of-a-kind simulation, but I'll run it one more time. Oops. Run it one more time for you. And so just especially this green and red region, you can watch as that green region gets eaten up as material flows across the boundary into the neighbors. And it sort of dissipates away. So there's plastic deformation that's happening here, but also, notably, there's no catastrophic breaks of any of the material. So it suggests that maybe pasta breaking strain is really, really large, and you don't get the kind of breaks you might need for crust shattering or star quakes. So those are sort of my two results, is just that I have this really enormous shear modulus in a material that doesn't tend to shatter.
Does that shear modulus correspond to closer to 10 to 13 or 10 to 14?
Come again?
That density, what density does that shear modulus correspond to, closer to 10 to 13 or 14?
I always take it to be somewhere in between there, but I think closer to maybe 10 to the 5, 10 to the 13 maybe. Maybe halfway to saturation. So these are the core results of that paper published in PRL. This was the great triumph of my postdoc in my time as a CITA fellow, was this paper, I think.
So then the breaking strain is about 10 to 30 roughly, or
The breaking
strain multiplied the epsilon by the shear modulus. The breaking stress.
The breaking stress, yes, yeah. Okay, the last thing I want to tell you about are sort of defects. These are going to be my Crackpot slides, where I'm going to put pictures side by side and sort of raise my eyebrows suggestively. And I believe that everybody can do this once before they start to get a reputation. And I choose to use my one very early in my career. So just bear with me for a moment. Most of the biological membranes in your body are composed of these things called phospholipids. They have a hydrophilic head and a hydrophobic tail, and they spontaneously assemble in an aqueous solution into these sorts of sheets. And don't they look sort of like lasagna? Okay, and I'm not just being like jokey and quippy with this. These phospholipids actually make a number of shapes that we can see in the pasta model as well. They make these spheres, which look a bit like gnocchi. These liposomes can have these bubbles, these voids inside of them, a bit like the Antinokey. And of course, they make these bilayer sheets. And if that doesn't convince you, they actually have these figures in their literature as well, which really match kind of our theory predictions too. The only difference is that their parameter, instead of density, they have the fraction of the solution that's aqueous relative to sort of phospholipids. It's really uncanny. And sure enough, they have those exact same defects that we do. On the left is an electron micrograph of the endoplasmic reticulum from a cell from the salivary gland of a mouse. This is observation. This is a real picture taken with an electron microscope. This is one of my simulations of pasta with those defects in it. And honestly, this is really striking. Like, something really weird has to be happening to have such a similar shape in common. If you notice, it's actually helical. The defect, if you sort of follow an edge along, is a helix that winds its way through the volume. Here it's easier to see because there's a single helix. We actually have sort of a double helix. There's a left-handed and a right-handed. It looks a bit like a parking garage where there's sort of two ramps that come up together as sort of these helices. Sure enough, that's actually the title of this paper. If you search parking garage structures, astrophysics, biophysics, this will come up. You'll find it. Oh, and I 3D printed it too. I highly recommend taking a look down the axis to see the helicity, so please pass that around. I had a summer student work on that one year. She made great progress with it. Okay, so why should these two structures be universal? Well, the biologists have this Hamiltonian for the surface energy or the bending energy of a membrane. They have these two energies, these bending moduli, and then they just integrate over sort of the mean curvature and the Gaussian curvature. And what you'll find for solutions for this, if K1 equals K2 is 0, if you just take a flat surface, this is 0, and that's a solution, and that's planes, right? That's kind of almost obvious. But what if K1 is equal to negative K2? In that case, your mean curvature term is still 0. It drops out. But then you get a minus sign from your Gaussian curvature, and that actually lowers the energy of the system. So there's a very natural reason to predict that a bit of hyperbolicity lowers the energy and makes it more favorable. So embedding a helix into planes gives you that little dose of hyperbolicity to lower the surface energy. So I haven't done this yet, but I've been thinking about doing this for a long time. a lot of models of nuclear physics can include a curvature energy, which they can fit from, for example, like fission barriers. This is when it would show up, is when you're getting away from kind of spherical nuclei. It would be really cool to go back and try and find one of these in the literature based on what's known experimentally, and then do what the biophysicists do using these simple Hamiltonians to get these surfaces instead of doing big MD simulations. That's a goal for the future, maybe using some sort of phase field model. Maybe I can do that at Illinois State, but I haven't done it yet. But the whole point is just that minimal surfaces minimize surface energy, and then a curvature energy can settle the tie. That's the whole idea here, and that kind of explains the universality of these self-assembling systems. OK, I'm out of time. And this is my penultimate slide, which is also a big divergence from everything before as well. In my free time, I do a lot of education and outreach, and I do it through YouTube. So every time you go on YouTube and you look at Minute Earth, Minute Physics, Kurzgesagt, or It's Okay to Be Smart, some scientist somewhere had to write that video. Some educator had to come up with that. So I'm a science writer for some of these channels. This is just the past 6 months of work from Kurzgesagt. And all of these videos have made an enormous impact with millions of people viewing them. And I'm not telling you this to brag. I'm telling you this to say that the only reason that a video about life under the icy surfaces of a rogue planet came about is because I have colleagues at the McGill Space Institute who work on exoplanets. And if you have really cool ideas that come from your research or otherwise, tell me about them, because this is where I get my ideas from, is from colleagues. And I'm here all week, so please come find me and pitch me the cool idea that you would like to tell to 10 million people. And maybe I can help you do that. OK. This is my summary slide, which I think is kind of boring. So I'll just kind of stop here and say thank you. And I appreciate your attention. And I'll take questions. Yes?
I wasn't sure the conclusion about the section of shear stress.
Yes.
That this is not particularly strong compared to this. Having passed the phase does not make elasticity or shear stress more stronger. So would you try to
Quite the opposite. Pasta has an enormously large shear modulus, is the takeaway.
But is it going to make any deformation in this?
It could make a deformation, yes. The size of the deformation is of order tens of centimeters on the neutron star surface.
That's huge.
Yeah.
How does it come about? So I guess I lost my logic. So this is value is what the shear modulus is.
I'm sorry, which value are you asking about? I'm a little lost too. What's your?
So what's the model magnitude result that give you 10 centimeters?
The shear modulus gives you a maximum height of like a mountain. Like this number converts to 10 centimeters for a maximum mountain height.
Isn't that comparable to the compressive?
Yeah, the compressive strength is going to be bigger. Yes.
The Neutron Stars crosses quickly 1,000 times.
So this is 1,000 times smaller than the compressive, and it still can make 10 centimeters.
Yes. This is how they report them as ellipticities in the gravitational wave literature. And so that's sort of the route that we went through. We get 10 to the minus like 5 or so, which comes out to 10 centimeters relative to the radius.
Working on magnetoid flares, I typically just normalize the shear modulus at about 10 to 14, not knowing what to do about that density. And when we talk, the 10 to 14 is already a bit too high to avoid pasta effects. Which
10 to the 14 what?
Grams per cubic centimeter.
That's, yeah, okay.
But the point is, though, that at 10 to 14, what is the breaking stress compared with a simple application of the BCC?
What's the breaking stress? Yeah,
If you just to take the standard BCC formulas and take a breaking strain of 0.1, what would the actual stress of your cluster be, breaking stress be in comparison?
Yeah, I guess the breaking stress is breaking strain times shear modulus, right?
Yeah.
And it would be that. So 10 to the 29 ergs per cubic centimeter. And though again, I'm saying that the breaking strain, the strain where you actually might get catastrophic failures, should be enormous. which might not be astrophysically achievable, at least in the pasta layer, meaning you would have to do the actual shattering in the ions above. We should talk about this more before I leave.
Well, I just want to get an overall sense of how much one should be scaled for strength. It doesn't sound like one needs to be scaled by much.
Not much, because if you go off of, for example, one of these plots, if you were extrapolating, then sure enough, my data point is right kind of here where it needs to be in order for all of these assumptions that I think people have been making for a long time to be good and valid.
Questions? You have a question?
Staring at me. So it's 10 times, so it's comparing to the ion Coulomb energy, you're saying it's like 10 times stronger.
Yes, in absolute terms, but it's also orders of magnitude and density. If you go up in order of magnitude and density, you go up in order of magnitude and shear modulus. Well, it's largely a Coulomb energy, yeah.
So Pascal or not, does it matter?
Probably not, but I would say that it should affect the breaking strain because it's a liquid crystal and it can flow and deform plastically much more easily than the crystal itself, or than the crystal above it, I should say. Yes?
So I imagine if you start with some surface normal surface with zero curvature, and you end up with a surface with a negative Gaussian curvature.
Oh, yes.
You can't do it with continuous deformation. So at what point do you have you have to have a phase transition or something? At what point do you move into the negative curvature region?
I'm sorry, could you walk me through that one more time?
So you can't get from zero to negative curvature with continuous deformation.
You need a topological transformation,
Yes,
that's right.
So I'm wondering at what point do you get this logical deformation, phase transition?
It's a good question, and it's having some topological barrier could give you multiple coexisting phases. Yeah, how you actually you drive the to tunnel to some topological new phase is a really good question.
Any more questions? If not, let's test our method again.